computer. Okay, so I'm recording. So as always, thanks a lot for joining us today. And let me start with, as always, with a presentation where I describe what we plan to do today. And then we will start with the exercises. So today's course, as I said in yesterday's mail, we will transform a 3D simulation. And the idea is that we start from geometrical height, and we want to compute the optical depth scale. And we will do it in parallel. So the idea is that we are going to repeat some of the steps of class day 6. So it's 2 classes before. But the idea is that now we are going to do it in parallel. So then it becomes much easier to handle bigger cubes. So in fact, today we will use the high spatial resolution sunspot simulation. In fact, we will see, as I mentioned in day 6, that in this simulation, the temperature at log tau 0, for example, or the intensity that we can compute from the simulation, it looks much better than the one from the low spatial resolution simulation. So I think things improved when they changed the spatial resolution. So for this reason, I want to use this one today so I can show it to you. And also, as we are doing things in parallel, everything becomes much more easy to handle and to execute. So I will start with a summary of class 6. It will be a brief summary, but some things are a bit different. So I will try to focus more on that part. And then after that, we will move to how to run the parallel wrap, what things we need, and how you can configure the input file so then you can run it. We will check the results, and then I will explain you some extra things that I do. And then, yes, so this is, I will cover very briefly what things you need to install for running the code. My idea is that I'm one of the probably youngest person using IDL, because I think most of you are already moving to Python or has already moved. And even older people like Han is already doing a lot of Python programming. So I think the requirements for installing the libraries and the packages that you need are something that probably most of you know how to do it. So then I will just show you the Readme file inside the distribution of the code. And then there you will see that there's a list of packages that you need to have. And then how you install those packages, I will leave it to you. But if at some point you don't know how to do it, or you have some problems, just let us know. I think in this case it's better to use Discord, because I think some people will just jump in and help you. But I think in this case, I will just not really focus too much on that. So I will just show you how to, which package you need to have. And then from there, I will just move. So then this was a very brief introduction. So then just let's move to the examples. So the idea is, as always, you will have in a folder, in this case, it will be day 8. And you will have some figures. We will go back to them later. But then I will copy 2 folders. One is this one, that is how do we transform, or we rewrite the original atmosphere to be ready for SER. And then here is how we run the parallel wrap for transforming atmosphere. So then let's start with this case. Here we just have a script. I put this one because it's the color table that I use. So in case you don't have it, I just put it here. And this is the output. So we are going to check how we configure this script to just produce this output. Okay, so then if we go to format, this is essentially the same script that we had from the 6. So I will not really go line by line. But I modified some things because we are using a different sunspot, so I mean a different run of the simulation. So I try to identify or highlight those lines where I modified things. So then you can check where I changed things and in fact compare with the previous one. Okay, so then the first thing is that you have to have the simulation, and I think, yes. So it's just go to the web page. Now it's working. And in fact, I think Chandrasekhar, he was the one that mentioned before that he could download the simulation. So in the first example, we use this one with a low spatial resolution. And for this example, we are going to use this one. So my impression, and I think I'm correct, is that both are the same simulation and run. But in this case, this is the full field of view, and you can see that each atmospheric parameter is very big. And this is just a cut of the central part. So then you have granulation in each side and the central part with penumbra and umbra. So, but I think the run has the same properties. So for this reason, we can start with this one because it's much more easy to handle. But at some point, if you want to have the full sunspot, just download this one. Okay, so then this again is from the Readme file on the web page, and I put modified because the dimensions are different. So now we have the full field of view is 4,000 times 4,000, but the slab, as I said, is just a cut, so it's 4,000. So the full horizontal domain. Well, I mean that direction. But then just a vertical, a small cut. So the vertical domain is 500 pixels. Then as the spatial resolution is, it's much higher also in the vertical domain. So we move from, I don't remember the number of points before, but now we have much more points in the vertical domain. And also this, it's different. So now we have 12 kilometers instead of 32. And this one is very important because we will use it later. And this is the vertical. So the step in the vertical domain, that is 8 kilometers. So I modified this. The rest is the same. So then just run until here. So I'm in this folder. Okay. So then it's going to read temperature. We will transform and transpose. So then, yes, let me just make this different. So this is the field of view that we have. And so as I said, it's a cut. So you have a granulation, penumbra, umbra, then the other side, the sunspot with penumbra and granulation. And for today, I will just work transforming everything and show you how to do it with the first 500 pixels. So we are going to cut here. So in fact, just let me see if I can make this a bit different. So if I do this, the program continues, and now it's loading the velocity and gas pressure. And remember that we are not only transposing, but also changing the sign. So then if you make a plot where positive is red, that means downflows, and negative is blue, that means upflow, you have that the red color is corresponds to the intergranules and the blue color corresponds to granules. So we are using the sign convention that SER needs, that is the opposite that the Mural code uses. And also here just have a check that the special features, so I mean the solar features now are much more complex and rich. So I think this is also interesting for just checking how the modelados, I mean the parallel wrap works, but also to have already a cube that we can use later, and it's interesting to use. And this is the full field of view that we will cover today. So it's 500 times 500 pixels. Okay, so then I will not cover, I will just go down. So this is the same. So we load the 3 components of the magnetic field, we transpose them, and then we compute the spherical. So we transform them to spherical coordinates because it's what we need. And then I think, yes, so then here is where we start the last part, where we have already everything in SER format, but we are going to save just a piece because this is what we are interested on. And this goes from 0 to 500 pixels. And then, yes, sorry, I forgot. And yeah, and I changed something here. So the vertical domain. So I mean, remember that we need to define the geometrical vector, the geometrical height vector, and it was not defined. So I just looked by eye, something that looked like z equals 0. And in this case, it's 150. I think in the previous one was 80. So this vector is now different. This value, it's not important. If you're starting 0 or another value, is not so important. But as Basilio reminded us in the previous telecom, it's important that the vector has the same step size. So then this step has to be updated here. And now it's 8 kilometers because it's the highest high spatial resolution. But I added this 150 just to have a reference 0. So then later we can make plots and check more or less how the temperature looks at that height. And then the rest is the same as in the previous class. And I think here, so we define the optical depth. Remember that it will be recomputed, but the top value, it will be kept. So just try to have a reasonable value here. And then we run a loop and we create fits file that has these properties. So it's X and Y, so the horizontal domain. Then this is the number of optical depth points. And these are the 11 depth dependent atmospheric parameters that we have in SER. So it's a temperature, optical depth, temperature, electron pressure, microturbulence, magnetic field strength, inclination, azimuth, geometrical height, gas density, and gas pressure and gas density. Okay, so then with that, we run the loop for all the pixels and we save this file. Okay, so we have just done the same step as in class 6, and it's only taking the simulation and put it in the proper format for running it in SER, and changing the sign of velocity and transposing the coordinates for having it as we need. But it was just that. So we are just repeating the same of the previous class. If you have any question, just let me know. And if not, we will move to what is new from this class. Okay, so then now we have computed this fits file. So now we move to the folder that I said before, that is this parallel modelador. So then here we have different files. The first one that we can start checking is this Readme file. So I have it here. So then it's in beta version. I think it's almost ready, but there are some things that may change. So let's say that is in beta. And then what I said before, so this is the necessary package that you need to have. So some of them are already included in some installations that you could have, and the others may not. So then just try to download all of them. And I think there are different options on how to do it, like with PIP or Anaconda or other options. So just again, if you don't know how to do it, just let us know. Do you want to say something, Ricardo? Oh, okay. so then this is just how to install the requirements or the required things for running the code. But now let's move to what you need to have in the folder for running the code. So then it says that in the folder, so in this case where I'm going to run it, you need to have the Python wrap, that is this one, is a parallel modelador. For other cases in the future, we will name it different, but for this one, it's just this name. And this is the Python wrap that will do everything. You can open it and check if you know Python. You can check how Ricardo did it, and if not, just leave it there. You don't need to open it. Then you need this initialization.input, that is the like the control file that we had for SER in the past. So with this file that I will show you later what it contains and what you need to write on it, we will tell the information to the computer of how many cores you will use, and what atmosphere you want to use, or what profiles and everything. So this will be like our configuration file. Then you also need to have a run files folder. So in this folder, you will include the necessary files for running the code. But in this case, as is the simplest example for running SER, we only need to have two files. So it will be the abundance file and the control file. So if we go there, we will have, this is the abundance, that is the same file that we have used in all the classes. And this is the control file. So we can go here. And you can see that is the same that we used in the previous class, yeah, 2 classes before. And is a file for running modelador. So you need to provide an atmosphere. In this case is input.mod. And the code will provide, we will do something with that atmosphere and will give you an output. In this case will be output.mod. And the code needs to have an abundance file for doing that operation. And what we'll do is what you are telling it here. So it's index 2. And you can check that index 2 means that is going to take geometrical height and gas pressure combination, and it will compute the optical depth and electron pressure combination from that. Okay, so then the idea is that after that the code will generate a folder that is called results, and there you will have the output of the program. And also you will have some error files. Okay, so then the concept before getting to run the program and everything. So the idea is that you will provide an atmosphere. So imagine that is 10 by 10 pixels, and then you will tell the code that you can use 10 cores, for example. So then the code will take the first 10 pixels from your atmosphere. It will distribute those 10 pixels in 10 different folders that will be run through different CPU cores. And in each subfolder, let's call it that way, it will make a copy of the run files, or I mean the files inside the run files. So it will be the abundance and the control file. And also it will include the atmosphere corresponding to that pixel. So in this case, it will be an atmosphere that is named input.mod. So each subfolder that is communicating with a different CPU, it's reading the atmosphere for a given pixel, and it's running this configuration file using this abundance file. So so the concept is basically sharing or repeating the task through different cores to do it in parallel. Okay, so then just let me check. Yes, and the output that will be, then for running the code, you need to just type this sentence. I will show you how to do it later, but it's just calling the Python wrap, and it will read what you have included in the initialization.input file, and it will just run. Then for our case, we need to provide as an input the atmosphere that we created. And as I said before, we already made it in the format required for the code, for the parallel wrap. So then it should be X, Y, where these are the horizontal domain, then optical depth, and then the 11 optical depth dependent atmospheric parameters. And then the output will be an array that is called like this, and it will be inside the folder results, and it will be the same format. So it will be X and Y, so I'm in the horizontal domain, optical depth, and then the 11 optical depth dependent atmospheric parameters. Okay, so then you go to the initialization.input file, and this is the simplest case later on, when we start with synthesis and inversions, it will be a bit more complex. So I wanted to start with the simplest case. And you can see that there's no many things that you need to provide. So the first one is the number of cores that you want to use. So then depending on your server, you can have 5, you can have 10, or you can have 50. Then you need to specify the input. So as you can see, we were in this folder and we created this fits file. So I'm telling the code, please read that fits file. Okay. And then you can tell the code how many pixels from that cube you want to transform, invert, or synthesize, depending on what you're doing. And this is through this command. So in a spatial position, you have the option of typing 1. That will be something like this. So you type 1 and you comment the other thing. And then with this, it will just take your full cube and will do the operation that you're trying to do for the full snapshot. Or you can just pick a different small field of view. So today, for the class, I will just do it in a small field of view just to show you how it works. But the figures that I will show you later and the other things that we will do later, I did it just typing 1. So I did the full field of view. Okay, so before checking how it works, let's also continue with the input that you need to provide. So in this case, you need to provide the atmospheric model header. So what this means is that if you remember, we need to provide a full atmosphere for SER for doing the transformation. And the full atmosphere means that you need to have the 11 columns, but also you have to have at the beginning 3 values. That is the microturbulence, the filling factor, and the straight line. So then we are always saving just the 11 columns. And I told you 2 weeks ago that it was that way because then you will provide them here. So you don't need to really save them as an extra parameter. And then you are just providing the values here. So you can put 1 for the microturbulence or another value for the filling factor or the straight line. In this case, as we are doing a transformation, it doesn't matter because the code will just work with the geometrical height, gas pressure, and temperature. And then from there, it will just run and compute the optical depth and electron pressure. But for synthesis, it's important. So when you're doing synthesis, if you are going to provide a cube like this one, so it will be X, Y, optical depth, and 11 columns. And then the values that you put here, it will be the values that will always appear in the header of each subpixel, each pixel that you have. Okay, so it's important to realize that what you put here, it will be then important. In the case of inversion, it will not matter because the inversions they need an atmosphere, an initial atmosphere from where you start doing inversions. And then that atmosphere will be located inside the run files folder. And there you will decide which combination you use. So this is only used for the forward modeling. So either transforming the atmosphere, although the code doesn't care about it, or when you're doing synthesis. And then the code will really consider it, mainly, for example, microturbulence. Okay, so but for now, 000 is fine. Then this sentence is if you are going to have the everything in the same folder, and for me it's always default, so I always use this as F. And then you need to provide the location where the modelador is located. So in this case, it's inside my SER distribution. So remember that you have to compile SER for doing synthesis, inversions, or response functions. But for the transforming the atmosphere, you need to compile modelador.x, modelador3.x. And then this is a fancy thing that Ricardo likes, that is that you can tell the code to send you an email when it's finished. So you can write your email address here, but in my case, I just don't want to be disturbed by, by my own computation. So but in general, basically with the first six items, you have already covered all the configuration that you need for running the code. Okay, so then let's save it like this. And we have that we can move to this folder. That is where we are. So we are parallel modelador. So then what I'm going to do is I want to be sure that I'm running Python 3, and then I just type Python 3, and then you call the file that it will run the code. So just type Python or Python 3, or just the file if you have configured your Python run properly. But in my case, I just always type Python 3 and then that, and then we just wait. The cube is a bit heavy because it's 500 times 500 pixels times 256 times 11, so it's like 6 GB. But after reading, then you will see, like it is now, it's really fast. So it's around 0.1 seconds per pixel. So then 50 times 50 pixels, it's usually around 20 seconds or something like that. You can see 30 seconds. Okay. So then we already have computed the optical depth for 50 times 50 pixels. Okay. So then, yes, maybe I can leave it like this. So where am I? Yeah. So then if we go to results, forget about this. We will go later to this. So the new things that the code created is this errors folder and this fits file. We can go through here. So if we go to results, then this error file, it does nothing inside, and then this atmosphere. So we can check what is inside. So yes, let's read it. Okay. Yes, wait a second.
Just to add that if something was wrong, this appears in errors folder.
Not necessarily, Vasily. So because
not always.
No. So if something goes wrong in the sense that the code stops, I mean, stops, and there's no output, then you will have an indication of which pixel had this problem. But as I will show later, sometimes you have a none number in the optical depth, and the code continue working and produce an output, but there's no error information. Because the error is when the code crashes. It could be RH or desired, so there's no output. But if the result is wrong, then there's no problem for the RAP to report. Yeah, thank you. Okay, so then we have red, and is 50 times 50 pixels, and then this is the vertical domain, and then 11 points. So then if we do a plot of what, sorry, TB frame is, and then tentatively it's around 150, and then let's plot temperature aspect. So this is just a bit part of the field of view where we have like some granule, intergranule. And the idea is that this is temperature, okay? And now we have optical depth. So if we plot 0, then we have an optical depth vector that now plotting at a given height, it's fluctuating because you know that we have a uniform geometrical height vector. So then the optical depth values for a fixed geometrical height, they will fluctuate due to temperature and magnetic field and everything. But you can see now that it has already finished and it's working, and you can pick other value, and then the distribution will be different. But we already have computed the results. Okay. So is there any question until this point? Okay, so then let me show you what the steps I recommend you to do after that. So, oh yeah, there's a chat. I don't know. So Ricardo, do you see the chat?
Not, I'm opening it now.
Yeah, it's about MPI run.
No, it doesn't use MPI at all. You just use internal Python package.
Yes.
So it's more, you don't need to communicate basically any information when you run the process. So we don't need to use MPI for this.
Yes.
So if you just install multiprocessor package on Python, you are ready to go. Plus the others, but yeah, exactly that one, Carlos. Yes, thank you.
Yes.
Yeah.
Yes.
The MPI used when you need to share information when you are running the process. In that case, the pixels are fully independent, so it's fine.
Yes. Yes. Okay. Thank you.
Thank you.
Okay. So then now let's move to this folder. So here I already run the full 500 times 500 pixels that I show you. So then we have, this is the output. And then there are several things that I will show you what are they. So then the idea is that after running the parallel wrap for all the pixels, I run this script called clean.pro, and I will show you why. So if we go to that folder, just 1 second. Okay, so we go, and then if you clean.pro, so it's going to read the cube and plot the optical depth. So you can see here is the index 0, and then it's a reference 150 pixel. So you can see that in general it's smooth, but they are like black dots. And those cases, as I was saying to Basilio, the code didn't crash, so the code just ran. But in those cases, sometimes the full optical depth vector, sometimes just some pixels of the optical depth vector, they are not numbers, or they are none. And maybe they are infinitive, or they are too big to be in the file. So then the code crashed there. So just I will make it bigger. So then the idea is, just let me copy this. Oh, I can just run. Sorry, no, this is not. I'm here. So sorry. So then just to make it bigger. So there are few pixels that you can see that they have a black dot. So then what I do is I just go pixel by pixel. Just let me comment this one. And the program, let's go through it, but it's very simple, and maybe you can do it in Python if you don't use IDL. So I just check the dimension just to be sure. And then I define this index because I want to know exactly how many points failed. So then the idea is that every time that we find a point that is wrong, I will add a number there. So then at the end, I will compare regarding the total number of points, how many points failed, because I want to be sure that it's something that is just unusual and it's not something that is common. Otherwise, we need to check with Basilio or for example, Matthias, if there's a problem either in the simulation or in the code. So then what I'm going to look is for none values. And then I'm using a routine from IDL that it will check if there's a number or a none. And if there's a none, then it will provide 0. So then I'm just looking for zeros, and just let me show. So this will stop for the first pixel that has a problem, it will stop. So just let me run it. And then the idea is that if I plot, print the optical depth for that value. So it's I, J, then all the optical depth points, and then the optical depth. So if I do print of that, yes. So then you will see that there are values, in fact, but if we go to deeper layers, at some point, the code start providing none values. So here, okay. So then I'm just looking for any pixel that at any optical depth point has a none value. And this is what I'm doing with this sentence. So if you have any question, just let me know, but it's just I wrote here some explanation, and the idea is that I look for that. And also, I think at some point with some simulation, I don't remember when, I sometimes saw temperature that was not reasonable and in fact was negative. So just in case, I also check the same. So I check if a temperature at some point, some height, it's lower than 0. And there I put a stop because I really want to, so in this case was for printing, but this one is a strong stop because I really want to know why there's a temperature that is wrong. But you will see that in this run, there's no pixel with that problem. So I just have it as a double check or a safe check, but it is not normal. But just in case, if you have a pixel with low temperature and it's original from the simulation, then you should probably contact the developers. And if it's after the transformation, then also contact us, because then we need to know why Sarah is happy putting the temperature negative. So then I will just print the pixels. You will see it's not, so just let me run it while I'm saying things, because it will take like 30 seconds or something like that. And then, as I said, I'm going to print the total number of pixels and the pixels that failed. So then you can see that the total number of pixels is 250,000, and the number of pixels that fail is 29. So then we can consider that is something negligible. So we just forget about this. And what I do is just replace the pixel for the near one. So I just, I think the lower down, the lower one. So then you can see that this is how it looks now. So then I just remove 29 pixels, or I mean, replace them for the closest pixel in 29 cases. So it's just to make it, I think, more, more reasonable. So then I save this file. So it's the same format and same information that we received from the parallel wrap. It's just that in some cases I remove one, I replace one pixel for the closest one. So just to keep it clean. Okay. So then at this point, what we have is that this is the optical depth for a fixed index. It means for a fixed geometrical height, the optical depth is fluctuating. But for SER, we need the opposite. We need to have that each index of our atmosphere should be an optical depth and should be uniform. Okay, so then we need to add a second step, and this case is an interpolation, as we did in 2 weeks ago. And now what I'm reading is the clean file, and I'm doing the same. So I'm just reading the dimension. Then I'm defining an optical depth vector that should be uniform. And in this case, I'm defining it from log tau 1 to 60 times 0.1. So it's going to be log tau minus 5. So this will be the end of the vector. So it will go from log tau 1 to minus 5. And I think this is reasonable for a photospheric synthesis or inversion. And the rest of the points, I will discard them. Okay, so then I just run the loop. And again, this is, so just let me run it while I'm talking. And this is a very simple thing. So we defined the optical depth that is uniform, and I'm just interpolating the different parameters, so temperature, electron pressure, microturbulence, magnetic field, and so on. And then also the optical depth for each pixel. And I'm interpolating them to a uniform optical depth. Okay. And then our new optical depth vector, it is equal, so log tau is equal to log tau 0 at index 10. So I'm going, when this computation finishes, I'm going to show you the spatial distribution of temperature at this new optical depth, fixed optical depth index, that it will be log tau 0. Okay, so then this is the result of the interpolation. Okay, so then we have moved from an original atmosphere that was in a given format, then we transform it to SER format, but it was with a uniform geometrical height vector. And for each point, then the optical depth was 218. And we computed this optical depth. We cleaned the atmosphere. And we also computed or interpolated this atmosphere to a uniform optical depth scale. So now for a fixed point, it's always a fixed optical depth. And then we have the opposite. So if I do this, and what I'm doing in the program after this stop is plotting the new interpolated atmosphere at the index 10, that is log tau 0, but I'm plotting index 8, that is geometrical height. So now this is how the geometrical height changes for the optical depth log tau 0. So then you have that it gets deeper in when the field is strong, and then it gets higher in the granules and the top of the granules. So now we have the opposite. So we started from uniform geometrical height, and now we have uniform optical depth, and the geometrical height is changing for a given optical depth value. Okay, so then at this point, this output, so this Muran snapshot clean and interpolated, is what we just need for running the synthesis of any Stokes profile. So then I already ran it for testing it, and I will show you the results later. But the idea is that you have them in here. You have several figures, and the idea is that this one is the comparison. Again, the upper layer was selected by eye, so more or less where it looks like granulation, and this lower row is the new computation for with a uniform optical depth. So this is how it looks, and then I computed the intensity for that region at intensity at 500 nanometers, and then, as I mentioned 2 weeks ago, with a high spatial resolution, there are basically no artifacts. We don't see these shapes that we saw in for the low resolution. So then you can see that it's very clean. Sometimes you can see something, but it's not as prominent as before. So then if you already have the resources, I recommend you to just use this one. But also if you want to have a bigger field of view and you don't want to use too much computational power or disk, then you can start with the low spatial resolution simulation or focus on small snapshots on this one. But you can see how it looks, and it looks very, very nice. I would say that is really good. Okay, so then let me go back to the presentation. So then my recommendation, try to run everything that I showed today. So then it means that you should download the slab, run, then transform it to SER format using the script. You can pick this field of view, or you can pick a smaller one or larger one. Then run the parallel wrap and compute the optical depth vector. But then after that, clean the cube. Usually it's just a few pixels. I tried yesterday 1000 times 1000, and it was 50 pixels that were wrong. But still, it's something that is better to just remove them. And the spatial resolution is so high that if you replace 1 pixel for the closest one, it's okay. And then interpolate the atmosphere to a uniform optical depth grid. The idea is that the newest version of SER and design, they will allow you to avoid this step. But I believe that also for plotting, sometimes it's better to have everything in a uniform optical depth grid, because you can make just cuts and say, okay, how the atmosphere looks at log tau 0. So then if you have everything in an interpolated uniform grid, it's much easier. So I think my recommendation is to always do that. And then, as I said, if you have problems installing packages or running the code, or if there's some error in that and you don't know what does it mean, just let us know, or just write it in the Discord channel. So then maybe us or maybe someone else can help you. And then the next class is to continue with the Python wraps. In this case, we are going to prepare everything for run a synthesis. So now the files that we need to put in the run files folder will be much more, but we will have more files with more configuration. So we will spend some time there. And the idea is that we will complete the process of the forward modeling. So it means that today we moved from this temperature at geometrical height approximately 0 to a temperature at log tau. So we did this transformation. And now the next step is to take this new atmosphere, run the synthesis, and for example, compute the spectral features like the continuum at 500 nanometers or the Stokes signals for 6301 or something like that. So the next step is from this new atmosphere to spectral features. Okay, and as always, the next class is next Friday. So I think there's a lot of time for questions, and I don't know if I went too fast. So maybe please just let me know if something was not clear or I did something that you don't understand. Because yeah, I think I went a bit fast. So please just ask anything that you don't understand or you want to double check.
Hi, Carlos. Here's Matthias.
Hi, Matthias.
I was just wondering, do you understand why once in a while the optical depth calculation fails? Is this that just there are temperature density values in the simulation which are outside table range or something like this? Because yes, when I run the simulation, I also compute the optical depth, and if that would fail while the simulation is running, the entire simulation would fail. So I assume it must be something with table bounds in the opacity table or something like that.
Yes. The idea is that I'm not sure, but I was thinking on selecting a few pixels and then send it to Basilio so he can rerun the computation, because it's maybe what you said, or maybe sometimes that the optical depth value, maybe it's too big and then it cannot be written in with the specific numbers that. So I mean the points that you can use for writing the optical depth is limited. So I don't know if in some cases it's just too big and then the code says I cannot write that point. So it could be something as simple as that, or it could be, as you said, that maybe it just falls in a given height range out of the opacities that Basilio can compute, and then it fails.
Yeah, yes. I suppose it's something like that. It's a silly thing that we can solve easily.
Yes.
I suppose that if the temperature reach some very high values, I don't know, for instance, over 100,000 Kelvin, something like that, cell is not prepared for this value and then it's crashing. But we can change to contemplate this case in order to even if the result is not accurate enough, it doesn't matter, because it's normally it is a very high log tau value that is not important for synthesis.
Yes. But thank you.
Mm-hmm.
Okay, so any questions or comments? Okay. So okay, so then I will stop sharing and I will just try to again revise what we did. So we start with the simulation and we adapt it to SER format. This is something that you have to do with any type of simulation. So if you use Bifrost, Mura, and Marcha, so the transformation is the same. So I keep it outside in a very simple IDL script. And then when you have everything in the proper format, then running the parallel wrap will be the same for any simulation. So if you have Mancha, Bifrost, Muran, or whatever code, it will be the same because you already have the input ready. And then the idea is, as a double check, I always check that the optical depth values are reasonable or there's no infinite numbers. And then after that, I interpolate to a uniform grid. And I do this because I think it's better for visualization, but also it was required before in the C code, although nowadays it's not needed. And then with that, you have your cube ready for running synthesis of any spectral line that SEER can treat or decide also. So I think this is all, yes, and this is just the process, but now you have to try to install the packages and everything required for running the parallel wrap. And there I just didn't enter because I knew that it will take time and it will depend on the computer, on the Python that you have installed and your capabilities. So I mean your knowledge about Python. So I decided to just leave it open. So if you are really an expert, then you will have it in 5 minutes. If you are a new user, then you may have trouble. And then in that case, just use Discord or just contact us and maybe Ricardo directly, and we will help you. Okay. So then so if there are no questions, then as always, thanks again for joining us on Fridays afternoons or mornings and in some cases. And I hope to see you next week. Okay.
Thanks and bye.
Thanks. Bye.
Bye-bye.
Ciao.
Bye-bye.
Bye.
Bye. Thank you.
Bye.
Bye, thank you.
Bye-bye. Thank you.
Ciao.
Thank you, bye.
Bye. Okay, I will stop recording.